Hello, this is Samuel with the Physics Focus, and this week I am quickly going to run through what moments are in physics. Now, what we mean by a moment is not a very short period of time, but the turning effect of a force. So, here we have, for example, let's say we're looking at this situation. This could be, for example, looking down on a gate from above. So it's hinged over here on the left, and I'm pulling on the gate with a force F. This distance here from the hinge to the point where I'm applying the force is D. And the formula for working out the turning effect is very simple. The moment equals force times distance. However, there's one important thing to note here. That distance there is what we call the perpendicular distance. I'll write that out. Times perpendicular distance. Now in this particular example that's not a problem, because the distance from the pivot to the force and the direction of action of the force are already at right angles to each other. This is a right angle just here. So this makes the calculation very simple. The moment is size of force times the distance. So let's say, for example, let's put some numbers in. Let's say I'm pulling with a force of 20 newtons, and the distance here is 1.6 meters. It's a big car-sized gate. And in that case, the moment is simply 20 newtons times 1.6 meters equals 32. 32 what unit? Well, we're taking newtons and multiplying by meters. So this is one of the situations where physics really does make sense. It's not particularly imaginative here. The units of moments are Newton meters. And that really is all there is to it for a simple situation like that. However, I'm now going to take a slightly different setup. Let's see if I can capture all of this picture. Right. Now let's imagine that instead of pulling straight out, I'm actually going to apply that force at an angle. So this angle here is, let's say 50 degrees. Now that force will partly have an effect of pulling the gate open, but it will also partly be pulling the gate back onto the hinge, which won't have any effect at all in terms of turning it. And the moment now will not be 32 Newton meters. It'll actually be a bit less. If you're not convinced, imagine taking this force here and turning the direction all the way around to there. If I'm pulling in that direction, I'm not going to have any effect on the gate at all. I'm just pulling it tighter against the hinge. So the further around I go, the less the effect gets, the turning effect. So how do we work it out? Have a look again at the formula for the moment here. Force times perpendicular distance. Now there are two ways we can do this. Both of them equally valid, and both of them will give you the same result. They'd better, otherwise one of them wouldn't be valid. One of the ways is to take this force and split it up into its two components, parallel to and perpendicular to the distance, the displacement from the hinge. Sorry, let's try that again. So we could take it and replace it with these two components here. That's supposed to be running parallel there. There we go, that's a bit better. This one along the bottom here, that component of the force is just pushing it in towards the gate. So we can ignore that one. That has no effect on the moment. This component of the force is the one we're interested in. So what we need to do to work that out is work out that component. By the way, if you're not sure about how to work out components of forces or components of vectors, drop me a line, use the feedback link on the email that I sent to you, and saying so, and I shall fit it in a future video. So now the moment is the perpendicular force, which is 20 newtons times sine 50 degrees, gives us that component there, times the distance, times 1.6 meters, which, give me a second, I'll just work out how much that comes to. I'm afraid I don't know the sine of 50 degrees in my head. I make that 24.5. Newton meters. So a bit less than it was with that size force at right angles. An alternative way to work this out would be, rather than taking the perpendicular component of the force, is to take the perpendicular component of the displacement here. And the way to think of that is, imagine this force here. Imagine taking that force and extending the line out, like so, and looking at where is the closest position, the closest distance between the pivot and that line. In other words, the distance where it meets at right angles. About there. Such that that is a right angle. Now here we have a right angle triangle here, with 50 degrees there, and the hypotenuse, the longest side, is 1.6 meters. We're interested in this green length here. So, the moment now is that distance, that green distance, which is 1.6 meters times sine of 50 degrees to give us the opposite side of that triangle. So that's 1.6 meters times sine 50 degrees. That's the distance multiplied by this force, which is 20 newtons. And now we are looking at a force and the perpendicular distance. So we can simply multiply them together now. 20 newtons. Look at that equation there, and this equation here. Hopefully you can see there's not an awful lot of difference between them. Just written out in a different order. 24.5 Newton meters. Right. So in short, to summarise, if you want a general formula for a moment, it is this. Moment of a force equals size of the force times the distance from the pivot, the actual distance from the pivot to the point of action of the force, times sine of the angle between them. Doesn't matter whether you work it out this way or that way, that's the general formula, just there. So, whichever way you find easiest to work out, you should always arrive at the same answer. Thanks for listening.